Hi, and welcome to another video using the law of exponential change. In this particular video, we're going to look at an example that involves carbon dating. So for this example, we have some information. Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. Before we start this problem, let's write down our growth or decay equation, which is y equals y naught times e to the kt. And recall that y is our ending amount. Y naught is our initial amount. In this particular problem, k is going to be our decay constant. And it should end up being less than 0 because this is a decay equation. And then t is the amount of time. Now, if you watched the last video, you should recall that we figured out that for half-life problems, k is going to equal the opposite of the natural log of 2 divided by t. So we can actually figure out what our constant equals here. It's going to be the opposite of the natural log of 2 divided by 5,700. Now, let's say you don't remember this, or you just didn't even know that this was a truth or a possibility. You can still arrive at this value for k before you actually do the problem. So in order to do this problem, we need to figure out what k is. Let's pretend we don't know this. So just let's think about what happens in terms of half-life. If we have an initial amount, say 10, and we'll call that our y naught, our initial amount. Our ending amount is going to be 5 after 5,700 years. Okay, we can use this information to find k. So we need to find this k before we actually worry about this 10%. We do know it here. It should end up being the same thing if we use this information. So we're just verifying that what we've got here is what we would get if we didn't know this little formula. So let's plug everything in. And after we've got this written, we want to solve for k. Again, here's where the half-life pops up. You get 1/2. You're going to take the natural log of both sides. And when you do that, the natural log and the exponential cancel, so we get 5,700 k over here, and remember this turns into the natural log of 1 minus the natural log of 2, which goes to 0, so you get the opposite of the natural log of 2, and then you're going to divide by 5,700, and if you look and see what we've got here, this matches exactly with what we said it would, which is what we've got here. Okay, so we verified that our k is what we thought it should be, and now we can rewrite our equation and actually work out our problem. So let's rewrite the equation using this k, and then I'm going to show you a little thing that we can do to simplify. Alright, so here's our rewritten equation. Now anytime you have an e as a base and an exponent with a natural log in it, you kind of want to put those two things together because they are inverses and they will take each other out, or they'll cancel each other out. So if we rewrite this as e to the natural log of 2, and remember the properties of exponents, if we multiply this to a bunch of stuff, we need to end up with this. So if we multiply this to the opposite of t divided by 5,700, when we multiply these two things together, we will end up with this. So that works out, and the reason we want to do that is because now we can actually say, hey, look, this e and this natural log, they cancel out, and we end up with just 2, which is a little bit nicer, and we have this negative t divided by 5,700 right there. So we've got y naught times this equals y. Okay, so now we can use the information in the original problem. We have a 10% decay, so if we start with 100%, we are going to have 90% left. Okay, we're going to let this 100% represent our y naught, and we're going to let this 90% represent our y, our ending amount. So let's go ahead and plug this information in and figure out how long that takes to happen. Instead of using percents, I'm going to change these into decimal form, so my y naught is going to be 1 times 2 to the negative t divided by 5,700 equals 90% is 0.9. And then let's solve this for t. Remember, you have to use the logarithms to get this exponent down. So when you do that, you get, oops, let me fix that. When you do that, you get the natural log of 0.9 equals negative t divided by 5,700 times the natural log of 2. And now we can solve for t. And when we do that, we end up with t is equal to negative natural log of 0.9 divided by natural log of 2 times 5,700. And at this point, you need a calculator to get a decimal approximation. So go ahead and put that in your calculator. When you get that in your calculator, you should end up with 866.417 years, which means our sample is that old. It's 866.417 years. That's how long it takes for just 10% of the substance to decay. All right, I hope this made sense to you. Keep watching.